So what else can you do with a life history table? Well, here's another example of a life history table. This is age in weeks. And the reason I'm doing a lot of these tables with different units is just to show you that you can. You can measure age in weeks, years, whatever you like. You can even measure it in age classes, where each step is not the same unit of time. But at any rate, the numbers are going to look pretty similar in each case. You've got the stage, in this case it goes from 0 to 9, and you've got survivorship here, which always starts at 1 and goes down, and that's what's graphed here. One really interesting thing, one very useful thing that you can do with life history or life tables like this is that you can add this variable here. And again, remember that we're only looking at females. Usually we're only looking at females when we do a life table like this. In this case, what researchers have recorded is the age-specific fecundity rate. The age-specific fecundity rate, that's M sub x. In the case of the vole, the species Migrotus agrestis, age-specific fecundity looks like this. It starts off very, very low because newborns generally don't give birth. There are very few individuals that give birth at the age of 8 weeks. And then most individuals give birth sometime between 16 weeks, it peaks at 24, and then starts dropping off pretty rapidly by the time you get to 40 weeks here, or stage 5. A few individuals continue reproducing long into old age. And this is a typical pattern for a fecundity curve. You have very, very low fecundity early on. There's some precocious individuals that reproduce early. Then there's a peak and it drops off steadily after that. Plants, on the other hand, often, this is typical for animals. Plants, on the other hand, often follow a different trend, one where fecundity after a certain age is constant or sometimes even increases the older the individual gets. From the data that's here, you can calculate some very useful numbers that have to do with population growth. Okay, so here is the fecundity curve. And if we multiply L sub x, survivorship, times M sub x, age-specific fecundity, for each age class, we get this number here, L sub x times M sub x. And if we add up all of those values across the entire lifespan, we get this number called R sub 0. Okay, so here are the different values for L sub x times M sub x for the different stages. You notice that at first, the red line and the blue line are very, very close together. Okay, but increasingly as time goes on, this line, this red line, is going to be a smaller percentage of this blue line. The reason for that is that individuals die as time goes on. Okay, and so even if an individual that made it to, say, 56 weeks of age would have a reasonably high number of offspring, so few individuals make it to that age that L sub x, M sub x is very low. Okay, why do we care about this? Because this is the average reproductive output of a single female over her lifespan in this population. You can think of it like this. When a baby vole is born, she doesn't know if she is going to live to the ripe old age of 72 weeks and have 12 offspring along the way, or whether she's going to die within a few days and have no offspring. Okay, but on average, this is what she can expect. She can expect to have the sum of Lx, Mx across all of these age classes. That's the number of offspring that she can expect to have over her lifespan. Okay, I want you to notice a couple of things here. This is generally, again, true for animals, is that the highest contribution to reproduction usually happens very soon after the age of first reproduction. Even if age-specific fecundity stays pretty high, because survivorship always drops from one year to the next or one age class to the next, this line is going to go down more rapidly than this one is. That's always happens. Okay, this quantity here, this capital R sub 0, does not look familiar to you. But actually, it's a very important part of a variable that you already know about. If you take big R sub 0, that's the sum of L sub x, M sub x, and you divide it by the generation, you take its natural log, and you divide it by the generation time, you get little r. And little r is the per capita rate of births minus deaths. It's the same little r that we've been dealing with in the context of the exponential and logistic equations. And this, in fact, is how this growth rate, this per capita population growth rate, is generally calculated. You look at age-specific survivorship and fecundity for a cohort of organisms. You build a life table like this, calculate big R sub 0, and from that you calculate little r. Generation time is something you can also get from this data. So for example, here, on average, a female will have, basically the average individual or female that makes it to age 8 weeks will have 0.65 offspring, and those 0.65 offspring will have been born after an 8-week generation time. Generation time is going to be different for all of these individuals. So basically, if you want to calculate generation time, you just need to take a weighted average of the dates on which you expect individuals to be born. I'm not going to go over the logic behind this. I'm just going to say this is the equation for average generation time. Okay, this is not the sort of thing that I would expect you, by the way, to calculate on an exam. What I want you to know is that, hey, you could calculate it from this life table. You could find little r from just the information that's shown here. So for example, you could use the data in this life table to calculate big R sub 0. We can calculate L sub x times M sub x for each age class. We add them up and we get 5.9. And then if we take that, take the natural log, divide by the generation time, which is calculated with this equation here, we get little r is equal to 0.07 individuals per week. That's how quickly the population is growing. One thing you might want to think about, and again, we talked about sort of where the behavior, we talked about the behavior of equations when you're looking at the logistic equation and the exponential equation. This is another place where I want you to know not sort of how to make these calculations, but I want you to understand how these equations behave. In particular, notice that this value for r is greater than 0. What does that mean in terms of whether a population is growing or shrinking? Okay, what does it mean when little r here equals 0? Okay, one thing you might want to think about in light of that is there's a cutoff value here. When r is equal to 0, a population is neither growing nor shrinking. If r is positive, the population is growing. If it's negative, the population is shrinking. You might want to think about what the values are where the behavior changes, where you go from a growing population to a population that's staying the same size to a population that's shrinking in terms of r sub 0. In other words, what sort of value for r sub 0 do you have to get for a population to be staying the same size? There is going to be a question on the quiz about that as well, so that's something you want to think about before you go into the quiz. Okay, another thing that I want you to be able to do with these equations is kind of manipulate them and get a sense of, the behavior in terms of what changes in these life history parameters increase fitness, because these are the parameters that natural selection is going to be tinkering with, essentially, in order to optimize the life history to get the greatest fitness it can. In other words, you're going to tend to see organisms out in the wild where these variables, these L sub x and M sub x, are set such that fitness is maximized over the lifespan. And it's pretty obvious what some of these changes that would maximize fitness are, although there are some subtle effects that we'll want to keep in mind. Obviously, one of the most important things for increasing the lifetime reproductive output of an organism is for it to increase its survival. Okay, organisms that die don't reproduce, and so it's extremely important that organisms survive to reproductive age. And you'll see lots of adaptations in organisms that help them survive to reproductive age. One thing that is very interesting here is that this contribution is somewhat equal to the contribution to lifetime reproductive fitness, this contribution drops off over time. The importance of making it to a certain age is basically proportional to how much of this curve you haven't gotten to yet. Okay, so there's very strong selection for making it from age 0 to age 1, because all of your reproductive capacity is in front of you. As individuals get older, though, more and more of this curve is behind them, and they have less reproductive potential ahead. So for example, at age class 5 here, most of the reproducing that an individual is going to do is behind it. There's relatively little possible reproduction left. When individual voles get to age class 7, it's even more extreme. Almost all of the reproductive potential is behind them, with very, very little up ahead. And this should sound familiar, because we talked about this in the lecture on conflict and cooperation. The conflict, basically the conflict that parents feel over altruism. You know, if, for example, if a duckling is being menaced by a runaway bicycle, does natural selection favor mallard fathers that rush out and try to save them from the bicyclist, or does it favor fathers that run away? And as mallard fathers get older, they have less of their reproductive potential ahead of them, and so increasingly natural selection favors the strategy of trying to save your current ducklings at whatever cost. It's the same idea here. As individuals age, there's less and less selective pressure, favoring adaptations that keep them alive even longer. And at some point, once you go completely beyond reproductive age, there's no selection pressure for adaptations that keep you alive any longer. This is a very interesting thing about human beings, by the way, that we generally do live beyond reproductive age, often well beyond reproductive age. And this is very interesting to evolutionary biologists, because there isn't a selective pressure for keeping you alive and healthy after your reproductive potential has fallen to 0. But to go back to our topic at hand, it really helps in terms of your lifetime reproductive output, your lifetime fitness, if you can survive to reproductive age. Increasing fecundity, of course, will also increase your lifetime reproductive output. That's not a surprise, but one thing that you might not have realized is that selection particularly favors increases in reproduction at early stages. And the reason is that individuals that make it to an early stage of reproduction might not survive to a later stage of reproduction. So the strategy, all else being equal, the strategy that is favored by natural selection is mature as quickly as possible and reproduce as quickly as possible once you are at maturity. Okay, there are some reasons why not all organisms do that, but there is a strong fitness advantage to individuals that can. Okay, so because survivorship is always falling, it's safest to get your offspring out and into the world early, because there's always the probability that you may not make it to the next breeding season. Let me just show this on the graph so you see the effect of it. If you have individuals, so if you have an allele in a population that causes individuals who are very young to have a much higher fecundity, it makes a big difference to this red curve. And remember, this red curve is what determines your lifetime reproductive output. Your lifetime reproductive output, and therefore fitness, is proportional to the area underneath this curve. And if we alter the fecundity at this point in time, you see there's a big shift. This red curve bulges upward noticeably. Okay, so you can see the difference there. Now let's suppose that there's a different allele in the population that causes a really big increase in fecundity much later in the lifespan. Let's see what effect that has on the red curve. Okay, there's this big spike up here, and the red curve almost changes not at all. And there's only a very, very small effect relative to the effect that you see if you change fecundity early on in life. And again, that's because very few individuals survive to experience the beneficial effects of this allele. So if you had these two alleles in competition with one another within a population, the allele that increases early fecundity would go to fixation, and this allele that increases late fecundity would not. Okay, so there is a lot of selection pressure favoring increased survivorship and increased fecundity early in the lifespan. There's one more way that you can increase fitness, and this one is surprisingly powerful. It's actually more powerful than changing survivorship or fecundity. It's changing generation time. So notice that both survivorship and fecundity go into big R sub 0 here. But over here, when you're calculating little r, you're taking the natural log of this number. And that makes changes in these variables much less influential. You don't take the natural log of t, the generation time. And what that means mathematically is that when you change t by 10%, it has a much bigger impact on little r than if you were to change survivorship or fecundity by 10%. In other words, little changes here matter more. The reason for this is that the sooner you can get offspring out into the world and growing up themselves, the more rapidly they will be able to reproduce. It's like putting money into the bank early in your career rather than late. If you put money into the bank earlier in your career, it has lots of time to gain interest, and that interest will start gaining interest. So you start the runaway process of exponential growth more quickly. That's the same effect that you get if you shorten generation time, and it's extremely powerful. In fact, I believe it's Einstein who said that compound interest is the most powerful force in the known universe. He had something, Einstein. He was a pretty clever guy. So to sum it up, if you can increase survivorship or fecundity early in the lifespan, it's better than increasing them late in the lifespan. And this is mainly because, by the way, when you increase survivorship and fecundity early in the lifespan, that's what shortens generation time. The more individuals that are being born early in the lifespan, those individuals have a very short generation time, and so that's going to skew generation time shorter. What's seen here is the sensitivity of changes to these, to little r. Basically, if you tweak m sub x, the stage-specific fecundity, or l sub x, the stage-specific survivorship. And the basic pattern here is kind of what you would expect. R becomes less and less sensitive to changes in these variables as the stage classes increase. The most dramatic changes that you can make in little r are by changing fecundity and survivorship very early on.